So we have here an example that I'm going to work through all the parts for this NMR problem. The problem is that we have C6H12O and we want to figure out what it is. And the first thing that we want to think through is about the degrees of unsaturation. So C6H12, that's missing two hydrogens because it would be C6H14. And that means there's 1 degree of unsaturation. There would be one double bond or one ring in this molecule. The oxygen can be doing several things. It can be an alcohol, it can be an ether between two carbons, or it can be part of a carbonyl group, which is a C double bond O. And if it's part of the carbonyl group, then that's the degree of unsaturation. And if it's not part of the carbonyl group, the double bond, then that's part of the other part of the molecule. Now we have both the C13 NMR and an H NMR spectrum here. I'm going to just work with the H NMR spectrum. So let's go click on that and take a peek. Okay, so here we've got this NMR spectrum. And we've got some stuff going on over here, and we got some stuff going on over here. And on this one, we can actually magnify them and take a better look. There's a total of 12 hydrogens. Down here, we can see the integration. We've got this one little unit of red here, and this is twice as much. So for these peaks, we've got a 1 to 2, which is most likely going to leave us with 9 more to go. And that's going to be over here. And over here, it looks like we have 2 blobs also. But it's a little bit hard to see what the ratios are going to be on that. So let's first characterize the 4 peaks. So this peak over here at 2.6 or so, let's go click on this area. This is the 2.6 peak, and this is the 2.4, 2.5 peak. That's the 1 to 2 peaks. This is a detail of this area right here. So for this one, we've got a multiplet, and we can see 5. There may be more. It's very small peak, so there could be some other ones we're not seeing, but it's not a quartet. It's 5 or more peaks. So for one hydrogen being split into a multiplet, and over here we have 2 hydrogens, so this height is of the integration is twice as high as that. And this is very definitely a quartet. We've got a 1 to 3 to 3 to 1. It's a very lovely little quartet there. Okay, so the first peak over here is a multiplet with 1 hydrogen. This peak over here is a quartet with 2 hydrogens. Now we've seen the quartet with 2 hydrogens, and it's pretty common to have an area 2 being split into a quartet, which implies that there's 3 hydrogens next door. So this could very well be a CH2 next to a CH3. That would be consistent. And this multiplet is going to be 1 hydrogen next to a bundle of hydrogens, not really sure how many. Now over here, over by 1, we have more peaks here. And here we've got this area right here is a doublet, and it's pretty big. The area on here is about 2/3 of this total height for the whole blob. So I'm going to assign that this is, if we had 9 hydrogens left to play with, we had the 1 to 2, and that would make this 9. I'm going to go with 6 and with 3. Okay, now I'm not doing that with a ruler right now, but could be done to get it roughly consistent with that. So the first one is we've got a doublet here. So we've got 6 hydrogens split into a doublet, means being split by 1 hydrogen. And if you recall, this peak, of course, has got 1 hydrogen. So it's highly likely to me that this 1 hydrogen peak and this 6 hydrogen peak are connected to one another, and we've seen that signature before. The 6 hydrogen peak being split into a doublet, the 1 hydrogen peak being split into a multiplet. And then this other one here, which is just above 1, is a triplet. And this is the one that I'm suggesting has an area of 3. And so 3 hydrogens split into a triplet implies next to 2 hydrogens. So we have 2 couplings here. We've got the 1 hydrogen and the 6 hydrogens that are splitting each other. And that's my best assignment here. And we've got the 3 hydrogens and the 2 hydrogens splitting each other. Also there. So that's where I'm going with this one, with 2 kinds of fragments that we can pick up out of here. Now, in addition, these 2 peaks over here, the 1 and the 2, those are shifted downfield. Those are going to be closer to whatever the interesting bit of this molecule is, which is going to involve the O. And these back here are further away, further isolated from the O and its section. So what I'm going to propose we have, the signatures that we have here with the 1 and 6 are a good signature for an isopropyl group. And then the 2 and the 3 are a good signature for an ethyl group. I'm going to show you those pictures in just a second. So an isopropyl group would have 3 carbons, an ethyl group would have 2 carbons, and that's 5, but we have a 6th doing something. And the isopropyl group is CH3, CH, CH3. Okay, so that is 7 total. And the ethyl group is CH2, CH3, 5 total. So the hydrogens are all taken care of, but we don't have a carbon dealt with and we don't have an oxygen dealt with in this spectrum. And we're not really sure where the double bond is unless it's between the carbon and the oxygen. And that's what I'm going to propose here. So clicking on over here, this is what I'm proposing. We have an ethyl group over here, the CH3 area 3 peak being split by the 2 hydrogens next door. The CH2 area 2 peak being split by the 3 hydrogens next door, that's the quartet. The isopropyl group, we've got 6 hydrogens. Again, we've seen that before, split by 1, and 1 hydrogen split by 6. So those are 2 pretty strong patterns in this NMR. And then we've got the carbonyl, which would give us the degree of unsaturation. So this is what I'm going to propose we've got, is that this is going to be over here. Of course, it doesn't really matter which side I attach it to. And obviously my molecular building here is a little bit awkward, but let's go see how this is going. So what do you think about that? So we would have 11, 12 hydrogens, 3, 4, 5, 6. We've got all the atoms. We've got the degree of unsaturation. This peak here, okay, and this peak here, the 2 and the 1 are closer to the carbonyl. Those are going to be downfield shifted. And this methyl and these 2 methyls are going to be further to the upfield section there. So for here versus there. So that's my proposed solution, and we're going to go back and see what the solution is. And look what they've got here. They've got the carbonyl in the middle. They've got the isopropyl group on this side, CH3, CH, CH3, connected to the C double bond O, connected to the CH2, CH3. That's how this is done.